Back in the day of 2D gaming, things were pretty straightforward. To move your character around, you just add the horizontal speed to their X position and the vertical speed to their Y position. It was all about programming logic and not so much about the math. Plus, you didn't have to deal with the nightmares of compilers, the good old days of programming and pure machine code. Every programmer's dream. When we shifted from 2D games to 3D games, the game physics and rendering got a whole lot trickier. Now we have to deal with an additional dimension, which will require trigonometry to achieve. Let's take an example. Imagine you have a character in a game. This character can move forward and rotate in any direction. Now, the direction the character is facing is represented by an angle, which we'll call the face angle. When the character moves forward, they're moving in a direction determined by the face angle, and this is where our friends sine and cosine come into play. To move the character, we change its x position by multiplying the sine of the face angle with the forward velocity, while simultaneously we change its z position by multiplying the cosine of the face angle with its forward velocity. Similarly, in 3D games, we have 3D animated characters, and each character is made up of various bones that can move and rotate independently. In most N64 games, each of these bones requires the use of 3 sine and 3 cosine functions to calculate the rotation. This is because each bone can rotate along 3 separate axes, with each axis needing 1 sine and 1 cosine to be calculated. And it's not just animated characters. All objects have to use these functions to calculate their visual rotation. So whether it's Mario turning his head, or the spinning platform, trigonometry is at work. Here's the tricky part. Accurately computing the sine or the cosine of a value is not easy. Sine is what we call a transcendental function. This is similar to how the value of pi goes on forever, without ever repeating. So we can't write down the exact value of the sine of most numbers. But don't worry, while we can't get the exact value, we can get as close as we want to the real result. It's just that every additional digit of accuracy is going to cost exponentially more resources. So because it's so tricky and expensive to calculate the exact sine or cosine of a value, computers have to use an approximation algorithm instead. Mario 64 was one of the first games to come across this issue. The way they handled it, or a variation of their method, became the standard for most N64 games. But what if I told you? There's room for improvement. I bet you wanna see how. You are going to learn a lot of math today, and you will like it. Before we dive into the math, I have to clarify something about Mario 64. It has a limited number of angles that it can represent. To help you visualize this, imagine if you had only 4 angles to work with. Now, what if we had 8 angles? And what about 16 angles? You get the idea. So how many angles are we actually working with in Mario 64? A whopping 65,536. And here's something you might not have noticed while playing. In gameplay, Mario only ever uses 4,096 out of those 65,536 angles. Shocking, right? But even with this limited number, it's more than enough for his players to not notice any restrictions. After all, the controller itself can't even handle all 65,536 possible angles. Mario's angle also loops back to 0 once it hits 65,536. This means that our sine function only needs to work within a fairly small range. So how does Mario 64 compute its 4096 sine and cosine values? The answer is, it doesn't. Instead of calculating each value, Mario 64 uses a clever shortcut. It has a large table that stores every 16th sine value. When it needs to calculate the sine of an angle, it rounds the angle to the multiple of 16 and then looks up the corresponding value in the table. Thanks to our limit of 4096 angles, this covers every angle that can be reached in the game perfectly. However, this method comes with a cost. To use this table, you need to store 4096 different sine values. This isn't that much luckily, since this only takes 4 kilobytes of memory, or about 0.1% of the N64's total memory without the expansion pack. When we're working with 65,536 angles, the cosine of an angle is equal to the sine of that angle plus 0x400. What does this mean for Mario 64? Well, it means that they could reuse the sine table as a cosine table by simply attaching the last 1024 cosine values to the table. And that is exactly what they did. This bumped up the total table size to 5 kilobytes. You might be thinking, hey, that's a pretty smart move. It's super fast and efficient. Surely it can't get any better than this. Well, hold on to your hats because it's about to get a whole lot more exciting than this and a whole lot faster. Let's take a step back and analyze how expensive it is to compute the sine and cosine using this method. On the N64, what really matters isn't the complexity of the computations, but the amount of the data that we transfer. That's because the whole system is typically bottlenecked by its slow memory. If you look up the N64 on Wikipedia, you'll see it claims the console has an astonishing memory speed of 565 megabytes per second. I don't know how they got that number, but in the real world, it's more like 75 megabytes per second. Mario 64's compiler settings weren't exactly top of the line, and it compiled the sine and cosine code into 8 instructions. But with some common sense optimizations, we can get this down to 5 instructions. 5 instructions translates to only 20 bytes of memory being cached when you run this code. In terms of function size, that's practically a drop in the ocean. It's as fast as you can hope to be with these calculations. But while retrieving data from the table seems super fast in isolation, there's a hidden cost that we need to consider. Every time we read from the table, we trigger a data transfer to the data cache. And since the N64 caches data in chunks of 16 bytes, we're effectively paying the cost of a 16-byte data transfer every time. There's also a small delay when starting a cache request. While we can't exactly quantify this delay in terms of data transfers, it's roughly equivalent to caching an additional 16 bytes. So when we add it all up, we find that the total cost for each sine and cosine calculation in Mario 64 comes to about 84 bytes. Let's take this a step further. In a typical game frame, we might run this function about 100 times. For each subsequent call, we don't need to recache the function. However, we'll still need to cache the new data. So our grand total for 100 sine calls and 100 cosine calls is 5 kilobytes of memory and 6,420 bytes of data transfer costs. Let's see how much we can get this down to. Let's take a look at one of Nintendo's later N64 games, Ocarina of Time. They managed to make a significant improvement in this algorithm by shortening the table. If we take a moment to consider the sine function, we can see that the function graph can be divided into 4 distinct parts. With some clever manipulation, each of these sections can be recreated by simply mirroring or flipping the graph around. Imagine taking the first quarter of the graph and mirroring it. Then you flip the whole graph on its head, and voila, we've just recreated the entire sine function with only a quarter of its original graph. This clever trick allows us to get away with storing only a fourth of the original values. This approach does come with a bit of trade-off. It adds quite a few of instructions to the sine and cosine functions. In my own implementation of this, I ended up with about 180 bytes of code. It significantly reduces the amount of memory you need, just 1 kilobyte. That's the fifth of what we previously needed. With fewer values in the mix, the likelihood of hitting a previously cached value increases tremendously. For simplicity's sake, let's assume that every angle is equally likely. After making 200 sine or cosine calls, the chance of not having to recache the value is going to be significant, easily over 20%. Remember, the N64 caches memory in multiples of 16 bytes, and each sine or cosine value is a 4-byte sized number. So reading a single value will cause 4 values to be cached. I ran some simulations and I found that after 100 sine and 100 cosine values, we've typically only caused 180 separate data cache transfers. Of course, in a real game scenario, some of these cached values will be invalidated and some angles will be more common than others. But for the sake of our discussion, this approximation should suffice. Using the same cost analysis we did earlier, in terms of data transfer, we're looking at 180 times 32 plus an additional 180. This method is definitely a game changer when it comes to memory savings, and it even offers a slight reduction in data transfer costs. The trade-off is that the larger code means we are performing significantly more computations to derive these values. Overall, I would consider this approach improvement, but only in scenarios where constrained by memory. Given that the N64 only had 4 megabytes of memory without the expansion pack, I can imagine that many N64 games would prefer a solution like this over Mario 64's. However, I had the crazy idea to make this lookup table concept even better. Instead of storing a quarter of a sine table, what if we only needed an eighth? We can actually get away with just using an eighth of a sine table. But there's a catch. we also need to add an eighth of a cosine table to it. Imagine the N64 is trying to read a value in the table right here. It will cache this entire line of numbers, but only one of the 4 numbers is actually being read. If we have the interwoven sine and cosine table, like I suggest, we can guarantee that by the time we need to compute the cosine of a number, it will already be in the cache, ready and waiting. I'm not sure if anyone else has ever used this approach, but I was thrilled when I came up with this. You might be wondering, but why is an eighth of a sine table enough? I thought we could only simplify the sine function to a quarter before. Great observation. Here's the trick. Pull the missing eighth of the sine table from the cosine table. I've run simulations on this new algorithm and the results are great. It only requires an average of 92 cache transfers. That's just over half as many as the previous method. Over 100 calls, this algorithm uses 16 times 92 plus 180 bytes of data transfers. It also needs a table of just 1 kilobyte. Put it all together and you've got an 80% improvement in memory usage and a 50% improvement in data transfers compared to the original Mario 64 algorithm. Yes, it's slightly more heavy computation-wise, but the trade-off is more than worth it. However, we are dealing with the N64 here. In this context, our CPU is like an underused star player. With my optimized source code, we can typically finish processing a frame in a speedy 16 milliseconds or less. But that's not even half the time we have per frame. So our CPU is just lounging around idly for around half the game's runtime. That is not good. We want to harness all our resources to their maximum potential. The challenge now is to find a solution that uses even less data than a quarter sine table without turning our beloved N64 into a smoky paperwhite. Get ready for some math. It's time to dive into the thrilling world of mathematical approximations. The most straightforward way to avoid having the game cache so much data is to simply calculate the sine on the fly. I mean, why not? It can't possibly be that expensive to get a reasonably accurate result, right? Well, the most tempting solution here might seem to be the Taylor series. You might think, why not just add the terms of the actual definition of the sine and keep adding terms until it's accurate enough? To even come close to accurately calculating the sine, we need to take our input to the power of 5. That is an expensive operation. And even after all that, we're still left with an unsightly error around pi divided by 2. So what does an error around pi divided by 2 really mean for us? It would cause actors to not walk in a straight line when you hold forward, which is really bad. Using the Taylor series in this way would also mean that all the sine and cosine values come out slightly too big, which looks very goofy on the animation side. On top of all that, the sheer computational cost of the sine function starts to become a real issue at this many computations. So where does that leave us? What other options do we have? One unique method for approximating sine and cosine was actually conceived in the 7th century by an Indian mathematician and astronomer named Bhaskara I. This formula has an intriguing characteristic. If you plug in x equals pi divided by 2, the result is 0. And for x equals 0, you get 1. This matches the cosine function exactly and prevents the kind of peculiar scaling anomalies we encountered with the Taylor series. Bhaskara's formula is also pretty cheap to compute. Once we have the cosine, we can easily derive the sine as well. We know that the sum of squares of sine and cosine is always equal to 1. This is a fundamental identity in trigonometry. So if we have the cosine, we can calculate the sine by finding the square root of 1 minus cosine squared. This is straightforward because the sine of the sine is easily determined. You might be thinking that calculating a square root could be a costly operation. But that's not the case with the N64. Computing a square root on the N64 is relatively inexpensive. It's not more expensive than a division operation, and it's only around 6 times as expensive as a multiplication. The maximum error of this approximation is acceptable for our purposes, such as animation rendering. With this function, we avoid the need to load data into the cache. This eliminates the associated data transfer costs. While there is a computational cost to running these calculations on a CPU, it's significantly cheaper than the data loading process. This function runs in only 28 assembly instructions to compute both the sine and the cosine of a number, equivalent to just 112 bytes of code. And since there's no more data loading required, that is the entire data loading cost that we have to pay to run this function 100 times. From that angle, this is a huge improvement. Unfortunately, Bhaskara's formula requires us to use a division, as opposed to the polynomials which can get away with only multiplication. Divisions are about 6 times as expensive as multiplications, so this kind of sucks, but it is still a lot better than reading from a table. Technically, this function could be optimized down to 27 instructions, but even modern compilers are not that great at optimization. So if we went with that, I'd have to re-implement this whole function in assembly. If you're curious, here's what the full Bhaskara approximation function looks like implemented in C. At the start, we perform some bit manipulation to determine whether we need to mirror our input value. Explaining this is gonna go a bit beyond the scope of the video, but have fun discussing in the comments as to why I have to do this. Next, we employ an assembly macro to construct our compiler to construct a value directly in the code. Our compiler can be a bit inefficient and might store and load values from memory if we don't do this, which, as we've discussed, is quite expensive. After that, we simply apply the Bhaskara formula. Lastly, we apply the sine from the earlier mirroring or flipping operation. We simply get the sine from the square root of 1 minus cosine squared, as I've discussed before. And lastly, we use another cool compiler trick to do a macro that enables us to return 2 values simultaneously instead of just one. This macro was generously provided by EasyAsPy. Huge shout out to her. I would never have figured out how to construct this macro on my own. This macro actually utilizes GCC's imaginary number extension, which I think is hilarious, because sine and cosine are related to imaginary numbers in the same way that our output values are related to imaginary numbers. It's just a random coincidence that this happened to be the best way of doing this. I want to underscore that returning 2 values with this method is not the same as returning a struct that holds 2 values, or anything similar. This macro actually places the value into hardware registers. This means we avoid the costly process of storing and retrieving anything from the stack. Moreover, it saves a significant number of instructions. I absolutely love it. Before we proceed further, it's important to note that executing cached code is not without costs. There's an overhead associated with having the CPU process all this information. The longer the CPU is running, the less efficient the memory read pipeline becomes. So while this method of computing sine values is considerably more cost effective than the previous one, we can't merely look at the size of the function and equate it to the cost of loading 112 bytes. Given that data transfers have now been reduced to negligible amounts, from this point forward, we'll primarily be focusing on the number of instructions our code contains and the number of cycles each instruction in our code takes. The next approximation formula I want to talk about was shared to me by EasyAsPy. So a big shout out to her for this as well. How does this formula work out? Remarkably well. We can execute this formula using just 20 free instructions. I was initially very confused as to where this formula came from, but then it hit me. This is the only third order odd polynomial that fulfills the conditions f from pi divided by 2 equals 1 and the derivative of f in pi divided by 2 equals 0. This was actually just polynomial spline interpolation from high school. And it's the best approach so far. This ensures that we hit 1 at 90 degrees and we hit 0 at 0. And moreover, it gives the curve that nice, pleasant sine fade out at pi divided by 2 without ever exceeding 1, avoiding odd scaling issues. As the universe would just so happen to have it, the coefficients for these polynomials happen to be very close to those of the Taylor series. This means that our approximation will be accurate around 0, even though we've designed our values to be accurate around pi divided by 2. The actual code for this approximation is actually quite similar to that of the Bhaskara approximation. The main difference lies in the formula we plug into the center of it. Unfortunately, this function is only a third as precise as Bhaskara's, but it removes 5 instructions from the functions, and more importantly, it eliminates the need for an expensive division. While this level of accuracy is perfectly adequate for graphical rendering, it might not be sufficient for gameplay mechanics. There's a risk that the direction you're gonna be holding is not gonna be the same that you're walking, and taking that risk is not worth it for a micro optimization like this. Initially, I thought we could enhance this function by minimizing the discrepancy between this and the actual sine function. This idea isn't new. In fact, it's a common approach known as the min-max approximation algorithm. What's interesting is that when I delved into Unreal Engine 5's source code out of curiosity, I discovered notes by developers stating that they used a min-max approximation algorithm for similar purposes. They used an 11th order polynomial, which is significantly more complex than our measly 3rd order polynomial, but the core idea is the same. I decided to take a dive into the world of numerics to find a third order polynomial that minimizes the maximum error, while still satisfying the condition of sine of pi divided by 2 equals 1. And by dive into numerics, I mean fuck around until I can get something that is anything more accurate, because that's what numerics really just is. After a fair amount of mathematical deductive work, and the best fit I managed to find was the following. On paper, or rather on the graph, this looks incredibly promising. Excitingly, this new formula trims the maximum error down to just 0.007, which makes this approximation just as accurate as Bhaskara's, but it's more efficient, requiring fewer instructions and most importantly no division. However, there's a catch. Using this function causes the local minimum to occur before pi divided by 2. Because of the shifted local minimum, the value of sine x can exceed 1. This excess could cause some animation bones to scale improperly, which would be pretty noticeable. The error for each bone would grow exponentially with each child bone, which looks hilarious, but it's really not what we want. And this is why I decided to just steer clear of the min-max approximation altogether. The results are just not good at these low polynomials. Given how great pi's third order polynomial worked, it seemed worth exploring a fifth order polynomial. In this case, we had the condition that the first derivative of the function at 0 equals 1 to our spline interpolation. Calculating the polynomial is actually quite straightforward. In Germany, we actually learned this in 9th grade in school, and I never expected anything I've learned in school to actually be a useful life skill, but here we are. We know our function is of the form f from x equals ax to the power 5 plus cx to the power 3 plus ex. We want our function to only meet 3 conditions, which gives us these 3 equations. At pi divided by 2, our function should be 1. At x equals pi divided by 2, the derivative should be 0. And at x equals 0, the derivative should be 1, which gives us this last equation, which easily simplifies to e equals 1. After solving these equations, the actual polynomials we get from this process looks like this. This polynomial is very close to the true sine function, without any of the odd behavior we saw with the Taylor series or the min-max approximation approaches. The maximum error for this polynomial is only 0.00004, which is 1/500th of the error that the third order function had. So with the error being that significantly smaller, how does the computation cost look? At first glance, it appears to require only 28 instructions, which is the same amount as the Bhaskara implementation, and it only adds 1 more multiplication and 1 more addition over the third order polynomial. But here's the catch. The coefficients for the polynomials are so small that they introduce an extraordinary amount of inaccuracy. The animations generated using this approach end up looking peculiar because the extremely small numbers cause problems. We can address this issue by resolving the polynomial and adding a scaling factor, although this does add 2 extra instructions. The result is a 30 instruction function. Yes, it's 2 more instructions than the Bhaskara approximation, and it doesn't require any division, so this ends up being faster and more accurate. While I'm satisfied with the accuracy of the previous implementation, it irks me that Bhaskara's approximation still holds the title for the most accurate function within 28 instructions or less. There's no way that a seemingly arbitrary arrangement of mathematical operations should yield the best function. So I dug deeper. Considering the error of the third order and the fifth order sine functions, the fourth order cosine function should be somewhere in between. So how did that turn out? The implementation requires only 27 instructions, saving on 1 multiplication. With the coefficients of this polynomial, we can take advantage of the fact that 1 is always stored in a hardware register in this repository. It requires fewer instructions than both Bhaskara and the fifth order sine function. It might also even be more accurate than the sine function because we have to take the polynomial to a lesser degree, and there will be less exponentially accumulating floating point inaccuracies. The maximum error of this function on the graph is only 0.0028, which is absolutely fantastic. I found myself oscillating between all 3 functions, the lookup table, the fourth order polynomial, and the third order polynomial. As I managed to shave off a couple of instructions on each one, I settled on easy as pie's math functions for the graphic thread and the fourth order polynomial for the gameplay thread. Easy as Pie's math formula is accurate enough for its inaccuracies to be imperceptible in the graphics rendering, and a fourth order cosine function provides the best mix of accuracy and performance for game mechanics that require precise calculations. If we need perfect accuracy, or we only need to call the function once at a time, the lookup table will be the fastest option. However, no such situation exists in a game like Mario 64. If we consider data transfers, the fourth order polynomial only costs 1/64 of what the original sine and cosine function costs for 100 calls. Additionally, we can eliminate the sine and cosine table altogether this way, saving a whole kilobyte of memory. However, it's crucial to keep in mind that we are running a lot more CPU instructions, which leads to less efficient memory repipelining, and as a result, the actual factor by which we are faster is going to be much smaller than 64. So after all this, how much time does this actually save in a frame? Around 200 microseconds most of the time. Just a fraction of a millisecond. This is 0.6% of the time that a frame takes. It might sound pitiful, but in such an optimized game, every additional percent is hard-earned, and I'm actually quite happy with the results. And to answer the question in the title, what is the best sine function on the N64? It depends. Between easy as Pie's polynomial, my fourth order cosine, and my interwoven LUT, I believe we cover every use case. Easy as Pie's solution is great for repeated calls that don't require super high accuracy. The fourth order cosine suits repeated calls that need high accuracy, while the LUT is ideal for either hyper accurate sines or one-off function calls. I hope you enjoyed this, and a shout out to my sponsor Brilliant.org. Would you like to learn more about these kinds of topics? Brilliant.org is a great way to learn math and computer science with tons of graphics and animations to help you along. Brilliant has thousands of lessons, including some of the similar topics to this video, and new lessons are added monthly. For example, you could take a look at this Calculus Fundamentals course that will explain the basics of sine and cosine and how to get the derivative of a function. To try everything Brilliant has to offer, free for a full 30 days, visit brilliant.org/Kaze Emanuar or click the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription.